Hello everyone, good evening. I'll share my screen so that you guys can see what I'm writing. Share screen with audio. Start broadcast. Yeah. So, good evening everyone. This is TA class of course Quantum Hall Effect. This course is being offered by NPTEL in 2025 August semester. Yeah. And in today's class, I'll be covering the quantum Hall effect associated with the graphene, its Landau level spectrum, and then how the Zeeman splitting and the Landau level spacing relate with each other, the effective mass of the graphene, and then going and talking about the typical carrier densities in the graphene, which we can induce through the gating. Apart from that, we will also be discussing the Fermi temperature corresponding to the graphene. One second. Yeah. So what I'll be discussing will be two deck in magnetic field, which we have already discussed in very brief. Then we'll be taking the graphene, which is carbon arranged in honeycomb lattice in magnetic field, and its Landau level. Landau levels. We'll be comparing the Zeeman splitting and the Landau level spacing energies. Remember, in case of two-dimensional electron gas, Zeeman splitting and the Landau level spacing, they are the same. But we'll see how they come in the case of the graphene. discussing in, in graphene. Then we will be discussing how to induce carriers in graphene. Then I'll be discussing the Fermi temperatures corresponding to graphene. Yeah. So these are the points which I'll be discussing in today's lecture. So dear class, if you have any doubt or question, you can ask in the comment section. I'll be happy to address that one. Yeah. So having said that, two deck in magnetic field. Yeah. So in order to be able to compare our results for graphene to the analog expression for this two-dimensional electron gas, we'll first discuss the energy spectrum of the two-dimensional electron gas in the magnetic field, and then we turn on to the graphene. And in this one, we'll be following the book by Landau and the Listis. So we consider a two-dimensional electron gas system of non-interacting. It means the electron interactions are not there in the system. Non-electron electrons with a parabolic dispersion, since 2 times electron has this h per k square by 2m, parabolic dispersion in xy plane. And then this is the point 1 of the system. It is exposed to perpendicular magnetic field B. That B is BZ cap. So the picture which you should have in your mind is, this is your 2 deck, for example, and in xy plane and the z direction you applied BZ magnetic field. So this is your x, this is your y, and then in the perpendicular direction you applied the z. The Hamiltonian operator of this kind of system can be written as 1 by 2m and P minus EA, where this A is the magnetic vector potential. EA square, E is the electronic charge, where M is the mass of electron, P is the canonical momentum, and A is magnetic vector potential, where relation between B and A is given as B is curl of A. And within Landau case, then in Landau case, for B equal to BZ cap, for B equal to BZ cap, I can choose the Landau case A to be minus BY x cap and 0. Now if you substitute it, this is 1, this is 2, substitute 2 in 1, what will happen? Here h you can write as py square by 2m plus half m omega c square y plus px by EB whole square. There we have defined a cyclotron frequency. Here we have defined a cyclotron frequency omega c equals to EB by m. Now this Hamiltonian, if you see equation number 3, this equation is 4. So equation number 3 has the form of harmonic oscillator, if you remember, and the minimum potential where the center is shifted by px by EB, right? It is half m omega c square y square. Instead of y square, it is y plus px by EB. So y is shifted by px by EB. Thus, the energy level of the system are those of the harmonic oscillator, right? And for that case, you can write the energy level of the system is h bar omega c n plus half, where n is the quantum number and n is non-negative integer. So instead of that's I should write energy. So energy will be En equal to. So this is the form of energy for two-dimensional electron gas in presence of the magnetic field. And if you see E0 will be h bar omega c by 2. Similarly, E1 will be h bar omega c 3 by 2. So if you draw these Landau levels as a function of n, so if this is your energy, right? So this will be n equal to 0, n equal to 1, n equal to 2, and so on. And they all are equally spaced by h bar omega c. This is for two-dimensional electron gas. And these quantized energy levels, they are known as these quantized energy levels are known as Landau levels. Yeah. So this is in case of a two-dimensional electron gas subjected to the magnetic field. This we have discussed earlier in earlier classes also. This is just a quick revisit so that we can compare the results of this results, this equation number 5 with that of the graphene. Now going on to graphene in the case of the magnetic field. A graphene in magnetic field. Yeah. So in this part, we will restrict ourselves to the low energy near the Dirac point, such that the system is well described by the Dirac equation. That is, in the region where energy is h bar k Vf, right? So all calculation in this part, which I will be doing, are performed for excitations near the k point, and similarly in the other value k prime, these can be obtained in the similar way, analogous way. So in order to account for the magnetic field, we assume a minimal coupling, and the Dirac equation, which was like E psi at k value R, was h bar Vf. It was like this, right? And without the magnetic field. Without the magnetic field, this is the equation. This gives you h bar k Vf essentially. But now, if you account for the magnetic field, then what will happen in your in your this energy equation? This vector potential will also introduce. So in B equal to 0, now infinite perpendicular magnetic field Bz cap in finite Bz cap. What will happen? Your Hamiltonian will read H bar Vf sigma I delta plus Ea, like similar to P plus Ea by C, right? Similar to that only. And psi k R equals to E psi k R. Yeah. So using now this Landau gauge, the solution of this equation has the generic form. So let me write using what I mean. Let me write using the Landau gauge. The solution of this equation, let me call it equation number 5 that I have called. This is equation number 6. This is equation number 7. Using the Landau gauge, the solution of equation 7 has the generic form, which is psi k r. You can write it as like phi k y, and then in the x direction it will be a plane wave. And with this answers the Dirac equation we can write, since it's a 2 by 2 matrix, we can write it like 0 del y minus k plus b ey by c minus del y minus k plus b ey by c, and then 0 phi k, of course phi ky equal to e phi ky. Now it is convenient to introduce the dimensionless variable, and that I will introduce in terms of the magnetic length. Magnetic length we all know is under root h bar by Eb, and so for convenience, let's introduce a dimensionless. What does mean by dimensionless? It's just a parameter which doesn't has the dimension. Variable Xi is equals to y by Lb minus Lb times kx. So y by Lb doesn't have dimension, minus Lb by kx minus Lb times kx also doesn't have the dimension, because k has the inverse of dimensions of inverse of the length, and where Lb is under root h bar by Eb, what we call the magnetic length. Now these eigenvalues will read like h bar omega c 0 1 by root 2 del by del psi plus psi 1 by root 2 minus del psi plus psi, and then 0 operating on the wave function phi k xi, and will giving the energy eigenvalues E, and then the E phi k xi. And here we have defined the cyclotron frequency, omega c under root 2 times Vf by Lb and Vf times under root 2 Eb by h bar. This is the cyclotron frequency here. Yeah. So the eigenstate of this equations are spinors, right? So which equation? I will write 7 and then 8. The eigenstates of this equation are spinors. So the phi n k is psi n minus 1 xi and plus minus psi n xi, where the first entry refers to the sublattice A and the second entry to sublattice B. Here. Second to sublattice B. And psi and xi are the solution of the one-dimensional harmonic oscillator with n being a positive integer. So the eigenstate of this analog matrix for the k prime point are given by, this is for the k, I've written the equation number 9 is for k. Now for k prime, you write it like psi n, okay, psi n k, psi n xi k prime is equals to plus minus psi n xi psi n minus 1 xi. So the many body Hamiltonian of graphene in a perpendicular magnetic field is thus given by Hk. So all these things has been derived by Maclaurin in 1946 or 56, I think. Yeah, even before the graphene was discovered, these things, the Landau spectrum of the graphene was derived, and later in 2004 it was the first time when graphene was realized, this first 2D material to perfect 2D material to ever exist. And after that, there are enormous study on the graphene, Landau levels, fractional quantum Hall, and all those things, which I'll be discussing. But I'll write the Hamiltonian corresponding to it. Since the translation symmetry in the y direction is broken by the Landau gauge, thus ky is not a quad quantum number here. So we'll keep the integration over the y coordinate while summing over the kx coordinate, because kx is a good quantum number in Fourier space, and one can write the Hamiltonian, this psi k, your wave function, at summation of all n e to the power I k xx and a n kx xi n minus 1 kx psi. Similarly, bn kx xi n kx, and with this expansion, the Hamiltonian you can play with, and that will read h bar k is equals to h bar omega c lb times del xi sum over kx n n prime, and then your raging operator a dagger n kx complex conjugate of psi n minus 1 kx xi bn, the complex conjugate of the dagger basically, and then psi and kx, yeah, and that will be multiplied with factor of 0 1 by root 2 del psi psi 1 by root 2 minus del psi plus psi 0 operating on, now this, that was bra, this is get, so kx psi n prime minus 1 kx psi b n prime So this prime is on n, not on the b. So there are so many terms, you should not confuse yourself. Then kx. Right. Now one can introduce, instead of 1 by root 2, let's introduce 1 by root 2 del psi plus psi is equals to operating on psi and prime kx psi is equals to under root n prime psi n prime minus 1 kx, and similarly 1 by root 2 minus del psi plus psi operating on psi n prime minus 1 kx psi is equals to under root n prime psi n prime kx. This will yield you the, if you solve this Hamiltonian, this will yield you the eigenvalues E plus minus is equals to plus minus h bar omega c square root of n. So if you just solve these ones, these Hamiltonian, you will get the energy eigenvalues to be E plus minus h bar omega c square root of n. So the point to note here is that in the two-dimensional electron gas, if, let me just mark this equation also now, 9, and this is equation number 10. Energy levels of graphene, Landau levels. Yeah. So the point to note here is that for graphene, your Landau levels are plus minus, so they can be positive and they can be negative in energies. But for your two-dimensional electron gas, they are always positive h bar omega c and plus half. That's the one key difference. There, your Landau level goes linearly with the n, right? But here, the Landau level goes square root of this quantum number n. So there is another difference. Now, the point to note here is that in case of the two-dimensional electron gas, okay, let me write comparing equation number 5, comparing Landau levels of graphene and 2-dig. So let me just create a column, graphene, 2-dig. For graphene, your Landau levels are given as En plus minus is plus minus h bar omega c square root of n. For two-dimensional electron gas, they are given as En is equals to h bar omega c n plus half. That's the one difference. Energies can be negative and positive both. These can be negative and positive, can be both. Energy can always be positive. When I mean by energy, the energy values corresponding to this En and En for the graphene. Then Landau levels are not equally spaced. Not equally spaced. What do I mean? I mean, if you subtract En plus 1 minus En, so it won't be a constant number. It will depend on both n plus 1 and n. So, but in case of the 2-dig, Landau levels are equally spaced. Spaced with spacing h bar omega c.
omega c is the cyclotron frequency EB by m. So these are the key difference for graphene. Uh, the Lambda levels are not equally spaced, but at higher energies they do get closer also. So these are the key differences. The another key difference here is like the existence of the zeroth Landau level. N equal to 0 is also allowed, and that gives energy E equal to 0. That is equally shared between the conduction and the valence band. Conduction means the positive energy, valence band means the negative energy. But here the zero energy level is not allowed. Landau level with zero energy is allowed. Landau level with zero energy is not possible in 2DEC. It's not allowed, right? The another point to note here is that from if you look at the wave functions, equation number 9 and this, let me call this 9b. If you look at the equation 9 and equation 9b, what you will find that the wave function of electron and holes in these Landau levels are fully localized in one of the sublattice of the honeycomb lattice. Since psi minus 1 basically, right, is 0, so the wave function at the k point is localized in the sublattice B, while the wave function at the k prime point is localized in sublattice A. What is mean is that there are k and k prime values, right? Why do we call them inequivalent? Here also this is the proof that the wave functions corresponding to the zeroth Landau level, so the one sublattice holds the levels of one value, another sublattice holds the levels of the another value, right? And in this way, the magnetic field does not break the inversion symmetry. And uh, the degeneracy of these Landau levels can also be estimated, like if we do for the uh, 2DEC system. So it will be EBL square by h bar pi, and degeneracy of Landau level. In graphene is nothing but EBL square by h bar pi, which you can rewrite as omega c square L square by 2 pi Vf square. So if you remember, degeneracy is given by essentially phi by phi naught, right? So phi is what? B times A, phi naught it was h by E. So E B A by h, right? Now you can write h into h bar into 2 pi, and area you can write to be L square basically, and then you have the degeneracy of the spin and the valley, and then if you solve it, so it essentially gives you EBL square by h bar pi. The L is the size of the system. Yeah. So if that is clear, then we'll move on to the next problem, which is So what did I say in the beginning? So the two deck in the magnetic field we have discussed. Graphene in magnetic field and its Landau levels we have discussed. Now we'll be comparing the uh, Zeeman splitting and the Landau level spacing in graphene. Now let's define the problem, which is like compare the Zeeman energy and Landau level spacing in case of graphene. So that's the question. Now we all know that the Zeeman energy is what, when you put the spins in the magnetic in the magnetic field, so their energies get split, right? And the difference between their energies, which is, let me call the Zeeman splitting, delta Ez. So this delta Ez will be given as Gs mu B times magnetic field, where Gs is Lambda G factor and mu B is, we all know that the Bohr magneton Eh bar by 2 mass of electron. So Lambda G factor for graphene is roughly 2. So the successive, basically if you write delta Ez, it will be Eh bar by Me times B, right? So that will be your equation number, let me call this will be question number 11 and this will be question number 12 for today's class. Now you can also calculate this so this is done for the Zeeman splitting, but you'll have to now calculate the Landau level spacing. So successive Landau level spacing. So delta E LL, let me call delta E LL and let me call it En plus 1 minus En. So this we have already discussed, H bar omega C and H bar Vf times, if you recall this equation number 10, plus minus H bar omega C square root of N plus 1 minus H bar omega C square root of N, right? Where omega C we define to be Vf times under root 2 Eb by H bar. So if you substitute this one also, ELN will be H bar Vf under root 2 E b by H bar times square root of N plus 1 minus square root of N. This is my question number 13. If I ask you to compare, what will you do? You will take ratio, take comparing equation number 12 and 13. So delta Ez or delta ELL will be E h bar b by me. So E h bar b by me, mass of electron, divided by h bar vf under root 2 EB by h bar under root n plus 1 minus under root n. Equation number 14. And if you solve it, delta Ez by delta ELL, this will be given by, so if you just take h bar goes off, and it will be EB by ME times under root h bar by 2 EB. This is, and with 1 by under root n plus 1 minus under root n. Now for lowest spacing, lowest Lambda level, n is equals to 0, that will give Ez by the ELL to be under root h bar EB by 2 and 1 by ME, and that will, if you compute the values, it will be roughly 3.19 into 10 power minus 3 times square root of b, where b will be in units of Tesla. So at b equal to 1 Tesla, 10 Tesla even, your delta Ez is just roughly 1%. And so Zeeman splitting is typically much smaller than the Landau level spacing. So Zeeman splitting in case of Landau levels is much less than Landau level separation. Yeah. So in this one, we compared the Zeeman splitting and the successive Landau level spacing in case of the graphene. Now, if this is clear, so let's revisit our today's goals. So we have compared the Zeeman splitting and the Landau levels spacing in the graphene. Now, one more question we can ask is how to induce carriers in the graphene. How you can induce carriers in the case of graphene? Because you have to change your uh, filling factors, new filling which is NH by EB, so you'll have to change your filling factor by either varying the N or B. And in case of the graphene, since it's a semi metal, so you can, it's a Dirac metal also, so you can tune the Fermi level by tuning the gate voltages, and that's what I will be discussing. So how to tune the Fermi level in the graphene. So here we essentially use the most used uh, technique in the case of, if I talk about in case of the experimental condensed matter in the recent days, that is by capacitor mechanism. What do I mean by capacitor mechanism? So if you have this flake of the graphene, and in this one you want to induce the carriers. What do I mean by induce by carriers? For example, you have your band dispersion of graphene like this. Let me draw it in some other color so that it becomes even relevant. This is your graphene, and you have your band dispersion which is linear. So this is E versus K. Yeah? Your Fermi level is here somewhere initially. Right? This is what I'm drawing it at the K point, either K or K prime, you can think. Now, how can I move EF? The way to do is, so let me just bring it on this side. If you start adding, if you start adding carriers in graphene, then starts adding or taking out carriers in graphene, then you can move higher or lower for taking out in energy or Fermi level. What do I mean? If you add the carriers, the electrons in the system, adding electrons in graphene, your Fermi level will be moved somewhere here because you will be adding electrons like this. So Fermi level will be EF moved up. If you remove electron in graphene, what will happen? Your Fermi level will go down because you have taken out the electrons here. So Fermi level will go down. So this is, with this way, by adding the electrons or by removing the electrons, one can move in higher or lower in the Fermi energy. Now the point comes, how can you add or remove carriers in graphene? And here comes the interesting part with the capacitor mechanism. Capacitor mechanism can help tune this Fermi level by allowing changing the number of carriers in graphene. Sheet of graphene. This is graphene, right? And you connect it, you ground it, the one end of it. Good. Now you take another metal plate, in between you use dielectric, like HBN. So a dielectric is an insulator which doesn't allow the current to pass through it. It's an insulator. And on the metal plate, you add some voltage V, and since this is the ground, it will connect here. Now, if I ask you what is the capacitance of this circuit and how it is related with the your voltage V and charges, so you can tell me that okay, here your charges are related by Q equals to CV, and Q I can write total number of charges times now charge of electron E is equals to C times V. Let me call this, let it be V. Now you can divide both side by area. Divide both side by area of sample, side by area of graphene. So this will be N by A. That this gives you carrier density essentially. N by A is what? Number of charge carriers per unit area times electronic charge is equals to C capacitance times V. N by A you write as, let me call this one as C1. So it should be C1 by A, where C1 is capacitance of circuit, capacitance. So this will be N equals to C by A, let me call it CBG, or let me call it just C. C1 by A, let me call it C. So N by A is carrier density, number of charge carriers per unit area, and C1 by A equals to C capacitance per unit area, per unit area. So C times V by E. So the point to note here is that you can change your carrier density N by changing the gate voltage in your system, right? Gate voltage VG, let me call it VG so that you can relate that it's gate, VG is gate voltage, VG is gate voltage applied. So by changing the gate voltage, one can essentially change the carrier density in the system. And you dope more of the carrier, you apply positive bias in the metal plate, you will be adding more of the electrons to the system, you will be in the conduction band. You take out the carriers. How you do it? You apply negative bias. And because of that, essentially, you are taking out electrons from graphene. Means you are going lower in the energy. It means you are in the valence band. You are going deep in the valence band. And that's how you can move in the conduction and the valence band. Now, if I ask you, okay, if you take, how does the resistance response of the graphenes will look like? It has this band, right? A linear band. So if I just draw it, it will be like this. This time let me call this axis as the E, and this axis as the K. Let me call, I just want to have it like this. And this is my K point. point at which the band touches. Now if I ask you, what will be the resistance response of the device? So you have your graphene, on bottom of which you have your metal gate. Here you have your dielectric, like an HVN, and this is your graphene. Between these 2 points, you measure the RXX, and this one you current source IS. This one is drain. Here you apply a bias VG, and this will go to the drain. Now if I ask you, how does RXX depends on VG? So if I ask you to take a curve of the resistance, so this is my resistance, this is my VG, this is VG equal to 0 and RXX equal to 0. So when you are deep down in the negative voltage, what it means, you are sitting somewhere here in the valence band. Let me call this valence band and this is conduction band, the positive energy. When you are sitting here deep in the negative here, your resistance will be very low, right? It will be very low, very low, very low, very low, very low. But when you come near to the K point, here the density of state is very less. Actually, it's zero. So what will happen if your density of state is zero there? Your Rx6 will peak at this point. And then if you keep adding the electron, it will be going to the conduction band and then will go like this. Rx6 versus Vg. Because at the K point, sharply at the K point, the available density of state is zero. And you know that sigma, that is conductivity, depends on n e mu. If you don't have any charge carrier n there, your sigma will be approaching zero, and it means your Rxx will peak, and that's what it is. So this is the typical resistance response of graphene device. It's even sharper. So let me just, it's even sharper. So whatever I draw is very broad at high temperatures, but at low temperatures it's very sharp. So ideally, if you see, it will be like peaking very sharply. Yeah, somewhere like this. So this is the typical response of the graphene device, resistance response, and from here only, by noticing the position of the RxX VG at which the RxX is peaking, you determine where your Dirac point is. So that's the typical resistance response of the device. Now if I ask you, okay, well, you are able to adjust your carry density, but how your energy will be going as a function of that? So how do how does how does carry density n depends on k wave vector and also on energy in case of graphene? So you know that the number of states available is given as the available space in units of uh, in the phase space of k and the real space. So it will be 1 by 2 pi square degeneracy factor g times area, real space area, that is a, times, yeah, d2k, and it will be 2 pi by h bar. Since it's d2k, so h bar won't be there, it's a 2 pi square. So n will be given as g is for graphene, g is 4 because 2 spin and 2 valley. So here is degeneracy. So n will be given as 1 by pi square n by a, that will be the carrier density n, and times d2k will be nothing but pi k square. And if you see it, it is essentially k is equals to under root n pi. So let me call this equation as equation number 13 and maybe 14, or let's 15, k under root n pi. Recalling the graphene dispersion, E is what? Plus minus h bar k Vf, and you can write E as plus minus h bar Vf times square root of n pi. So by changing the n that you do by getting the sample, one can change the energy, Fermi energy E, and that goes as plus minus E h bar Vf under root n pi, where V value of Vf, Fermi velocity, we have discussed it earlier in previous class, 1 into 10 power 6 meter per second roughly, that is 3 order of magnitude, 2 order of magnitude, I mean 3 into 300 times less than the speed of light. So you can realize the physics, the kinetic physics, basically all those things. In case of the graphene, the quantum QED, quantum electrodynamics in the this condensed matter system, and this turned out to be very well nice, and that's what it is. Now, apart from that, now we can discuss, okay, what are the typical carrier densities which we achieve in case of the graphene? What are what is the Fermi temperature? Or let me ask, what is the Fermi temperature in graphene? So to address this one, first we'll have to address what are the typical carrier densities. And the typical carrier densities n are roughly of the order of 10 power 16 per meter square. 1 into 10 power 16 per meter square. Now, since you know this number, you can write E is equals to plus minus h bar Vf times, okay, let me just consider the conduction band only, EC, h bar Vf times square root of 110 power 16 times pi EC, and for Fermi temperature, EC will be equals to kBT. So T will be essentially h bar Vf by kb times square root of 10 power pi times 10 power 16, right? So if you solve this one, your T will, if you put substitute 1.05 into 10 power 16, 10 power minus 34, Vf is 1 into 10 power 6, Kb is 1.38 into 10 power minus 23, 100 pi is 22 by 7 into 10 power 16. If you do this maths, this T will roughly turn out to be of the order of 10 power 3 Kelvin. Area EF will be roughly what I'm calling the EC will be 0.12 EV, right? 120 MeV, and the temperature, corresponding temperature will be 10 power 3 Kelvin, 1000 Kelvin. So that's a typical Fermi temperature in case of the graphene, right? And this is all about the case of the graphene. Now graphene dispersion is massless, that you know. It has a linear dispersion. And this is about the, so how to induce carrier in the graphene. This we have discussed in this class. And the last part, the Fermi temperature corresponding to graphene, this we also discussed. So just a quick recap what we have learned in this class. First, in the two-dimensional electron gas in a magnetic field, how the Landau levels gets formed, how your magnetic vector potential comes in your Hamiltonian, and that gives you harmonic oscillator form. There the energy levels are of that like a harmonic oscillator, equally spaced, discrete. This is, and the positive, zero energy is not allowed, minimum energy is h bar omega c by 2. But in case of the graphene, if you solve it, what you find is your Landau spectrum is plus minus h bar omega c square root of n. So instead of equally spaced, it depends on the n, and as goes as n to the power half instead of linear in n. That's one difference. Then the negative energies are also allowed, which are not there allowed in case of the two-dimensional electron gas. Then energy, here the Landau levels are not equally spaced, but in case of 2D they are equally spaced. Here Landau level with zero energy is allowed, but here in case of the two-dimensional electron gas, Landau levels with the zero energies are not allowed. Minimum energy is h bar omega c by 2. So that's the vital difference between the graphene, the conventional uh, Landau levels of the graphene and the 2D. So then now I also come like how you distinguish from the Landau level spectrum of the 2D and the graphene. Then the degeneracy of the Landau levels I discussed. I compared the Zeeman energy and the Landau level spacing in case of the graphene, and we find that the Zeeman splitting is very less compared to the Landau level spacing in case of the graphene, even at 10 Tesla. Then we go on studying how to tune the Fermi level in the case of the graphene. Here we discussed that if you add more of the carriers, you move higher in the energy. If you take out more of the carriers, you go lower in the valence band or lower in the energy. And this you do by using a capacitor dielectric in between a metal plate and the graphene. You ground the graphene and you apply potential on the metal plate. That essentially allows you to tune your carrier density in the system. Then we also looked at how does the resistance response of these graphene devices looks like, right? Why the resistance peaks near the charge parity point or the Dirac point. The reason is being very simple. Your density of state is zero there. Your carriers are essentially your carriers are not there. Ideally, the resistance should be infinite, large, but that's not the case because your impurities, scatterers are there, which allows through the hoppings basically the Mott insulators. If you understand the Froslovsky, those hopping they do the conductions, and through those points only the conduction happen. That's why the resistance is very high. Then we go on studying like the how does the carrier density n depends on the k, which is the wave vector, and also how it is related to the energy of the graphene. So this we discussed, and then we derived. Then we also discuss what is the corresponding Fermi temperature in case of the graphene when you are typical carrier density of 1 into 10 power 16, which is very easily achieved with the gating. Now there is something else. How does or how do you distinguish? How do graphene Landau level spectrum looks like as a function of filling factor? So the point to note here is that if you measure the Landau levels of the graphene, the conductance, what will you find is on the electron side, here this is the zeroth. After that, there will be 2, 6, 10, 14. So this is my gxy 14 e square in units of e square by h, 14, 10, 6, 2. So if you measure the conductance in the case of the graphene at low magnetic field, when the splitting, when you have not lifted the spin and the valley degeneracy, in that case, this is the graphene conductance response. Your x-axis is carrier density n. For bilayer graphene, it will be different. For this is for the graphene. Bilayer graphene has parabolic dispersion. It has different Landau level spectrum. I will just draw this spectrum. So how do you distinguish from the Landau level spectrum? Let me just resize it and erase this one because this size is too big. This is graphene conductance response at low magnetic field, low B, when spin and valley are not lifted. Valley degeneracy is not lifted. That's why you see the filling factor nu is differ by 4. So between -2 and 2 there is a difference of 4. Between 2 and 6 there is a difference of 4. Between 10 and 6 there is a difference of 4. Not lifted. Then for the bilayer graphene it will be slightly different. It is totally different actually. That's why you can distinguish between them. They are topologically different. So instead of 2 here, in case of the bilayer graphene, this will be actually I should draw it uh, fresh because bilayer graphene is totally different. It's not like single layer graphene. Here also I should have these lines slightly down here because initially it's 0 to 2 is only space of 2. Right? Similarly here. Yeah. But for case of the bilayer graphene, it will be jump of 4, then stable, then jump of 4, stable, then jump of 4, stable, then jump of 4, plateau, jump of 4, plateau, jump of 4, plateau, jump of 4, plateau, or 4 plateau, like this. This plateau will be 4, 8, 12, 16, -4, -8, -12, -16. So if you see, this is bilayer like, bilayer Landau level at small b. At high B, of course, if you lift the degeneracy, then there will be 1, 2, 3, 4, all will be there. But at low magnetic field, the single layer graphene will show the conductance, which will be quantized in units of 2 E square by H, whereas the bilayer will show in units of 4 E square by H. So the point to note here is that in case of the bilayer graphene, the zeroth Landau level is 8-fold degenerate. If you see the zeroth Landau level, there is a jump from -4 to 4. But in case of the single layer graphene, the zeroth Landau level is only 4-fold degenerate. So there's a difference between the degeneracies also for the single layer graphene and the bilayer graphene for the zeroth Landau level, and that 8-fold degeneracy comes from 2 spin, 2 valley, and the 2 layer orbital basically what you call for the bilayer graphene. But for single layer graphene, since it's a single layer, so it has only two spin and two valids, and let's see for the zeroth Landau level. And that's the vital difference between these two. That's why the linear bends, the property of the linear bends is like they will be having a Berry phase of pi and will be giving Landau level spectra, which will be 4m plus 2. Here, your nu m, your conductance is gxy, nu slg e square by h. SLG means for the single layer graphene, and gxy nu blg e square by h. So where nu slg will be taking values 4m plus 2, where m belongs to integer, where nu blg will take values 4m, where m belongs to integer. Also, this has Berry phase of Berry phase is a phase which we already discussed in the previous class, that a carrier acquires when it moves in a in, along a path in a magnetic field. So this is the Berry phase. It can be magnetic field or anything within the adiabatic process. Berry phase of pi. This has Berry phase of 2 pi, essentially like 0. Berry phase of 2 pi. Yeah. So these are the key differences between these two. So in today's class, we discussed the Landau level spectra of 2DAG, Landau level spectra of graphene. We compared those two spectra, how they do differ. Then we we discussed the part, okay, how the Zeeman splitting and the Landau levels splitting differ in case of the graphene, because we know in the 2DAG we derived that they are same essentially, but here they are very different. That's why it's an interesting system, because you can essentially study those states independently. Then now comes the point, we determined how we can induce carriers in the graphene and can move in the energy band spectrum of the graphene. Then we discussed, okay, what are the typical Fermi temperature corresponding to the carrier densities in the case of graphene, how do the energy depends on the carrier density n. And then at the last, we discussed how do you distinguish the graphene device, if you have a graphene and bilayer graphene device, by measuring its conductance. So if you measure its conductance in presence of the finite magnetic field by sweeping the carrier density n, and then you get your quantization in the conductance, and from those conductance quantization you can tell whether it's a single layer or the bilayer. So this is essential tool which has been used worldwide to distinguish between the single layer and the bilayer devices. And since for trilayer it's slightly different, slightly complicated, but yeah, these two are very well separated, because 2 and 4 e square by h, they are very well different from each other. Remember, 1 e square by h corresponds to resistance of 25 kilo ohm. H by e square is 25 kilo ohm, 25.8 kilo ohm. So that's all. So with this one, I will conclude the class. If you have any doubt, question, suggestion, you can ask me in the comment section. I'll be happy to address your concerns. With this one, I'm Mohit, and I'll be signing off. And we'll see you in the next class. If you don't have any question, thank you for being there and attending the class.